Hello and welcome to the Evidence for Shells tutorial on OCR AS Chemistry. So first off we're going to talk about plasma TVs. So why are we talking about plasma TVs? Because plasma TVs have really tiny glass cells and they contain neon and xenon, and once you excite them they turn into ions, and these mixture of positive ions and negative electrons or plasma can emit light, so you can see your TV. And definitions now. First, ionization energy of an element is the energy required to remove one electron from each atom. 1 mole of gaseous atoms to form 1 mole of gaseous 1 plus ions. And ionic equations are fairly simple, as they are the element to make the ion plus 1 mole of electrons, and they always must be gaseous. Gaseous. So neon makes neon plus E minus, and xenon makes xenon plus ions plus E minus. So now we move on to part 2. And what factors affect ionization energy? Well, the atomic radius, as the greater the atomic radius, the smaller the nuclear attraction experienced by the outer electrons. The nuclear charge, the greater the nuclear charge, the greater the attractive force on the outer electrons. And electron shielding is the inner shells of the electrons repelling the outer shell electrons. The repelling effect is called electron shielding. The more inner shells there are, the larger the shielding effect and the smaller the nuclear attraction. So electron shielding is the repulsion between electrons in their different inner shells. Shielding reduces the net attractive force from the positive nucleus on the outer shell electrons. So if we look at our sodium equation again, it's 1 mole of gaseous atoms to make 1 mole of sodium plus ions to make 1 mole of electrons. But it also requires energy, lots and lots of it. So 496 kilojoules is required for this particular ionization energy. So we'll look at part 2 now. Lithium can have successive ionization energies which require even more energy in order to make 2 plus ions and 3 plus ions, say. And successive ionization energies are a measure of energy required to remove each electron in turn. This is an example, so this is not part of the definition. You just need to remember that part there at the top. So if you look at this graph here, at the 5th ionization energy, it becomes the energy requirement becomes so high that lithium can only have a maximum ionization energy of 5. So 5 electrons can be removed for lithium. And as the distance of each electrons from the nucleus decreases slightly, the nuclear attraction increases, so more ionization energy is needed to remove each successive electron. Moving on to part 4 now, we're looking at principal quantum number, which indicates the shell that electrons can occupy. This is shells and orbitals now. So an electron shell is a group of atomic orbitals with the same principal quantum number n, also known as a main energy level. And principal quantum number is a number representing the relative overall energy of each orbital, which increases with distance from the nucleus. The sets of orbitals with the same n value are referred to as electron shells or energy levels. Different shells are different principal quantum numbers. So the larger the value of n you have, the further the shell from the nucleus and the higher the energy level it is. So looking at the shapes of them, rules govern where electrons are allowed to occupy. Electrons include orbitals, which which is a region where electrons are found. S orbitals are spherical orbitals, and they gradually get bigger as you work away from the nucleus. P orbitals are sort of oblong shaped things. My chemistry teacher tends to call them elephant ears, don't ask, but they're sort of like dumbbells, and this is where the electrons occupy. I don't go round in that shape because they're like a cloud. They move around in that exact region, and it can each one of these orbitals can hold up to 2 electrons with opposite spins, so they go in opposite directions. So one electron can go this way, and the other electron can go that way. They can't go in the same direction because they have a negative charge, and they must repel each other. Going back to principal quantum number now. If n equals 1, then 2 electrons can occupy the shell. If n equals 2, then 8 can occupy the shell. If n equals 3, then 18 can occupy the shell. And then if n equals 4, 32 electrons can occupy the shell. So, finally, we look at represented electrons in orbitals. So, using these boxes, we can represent spins of electrons. And as I mentioned before, they cannot have the same direction. And the different blocks can hold up to different types of orbitals. So a d block can hold up to 10 electrons. 1, 2, 3, 4, 5, and up to 2 electrons in each one. I'll just use little ones to represent it, and the arrows, because there must be in different directions. Drawing it this way is the easiest way if you're asked to represent it. And they gradually work up in levels, starting from the lowest with S and P, working all the way up to D and F here. We will learn more about that next tutorial, so I hope you found this video useful, and we'll look more into these energy levels and where they lie exactly next time.